Our fourth speaker this morning is Jocienne Nelson from the Department of Physics and Astronomy at Oberlin College. She worked within the lab of Stephen Fitzgerald there and has collaborators within the departments of Physics and Astronomy and Chemistry and Biochemistry also at Oberlin. And the title of her talk will be Hydrogen Catalyzation in Metal Organic Frameworks.
So before I get to the specific reaction that we're catalyzing, I want to give you guys a quick introduction to what metal organic frameworks are, what catalyzation is, the sort of trapped hydrogen dynamics that we see in metal organic frameworks, and how we experimentally detect them using infrared spectroscopy and mass spectroscopy, and then I'll show you a bit of our results. So, metal organic frameworks are nanoporous crystalline materials. This means they have a very highly defined crystalline structure, so you know where everything is. They're useful for gas storage, so potentially hydrogen storage for fuel cells. They're just powder, so it's something you could take in your car maybe. Gas separation, so separating out gases by different sizes or other parameters. And then what we're interested in right now, which is catalyzation, so breaking the bonds between molecules. We have a very large internal surface area. Here's the yellow here is the space that the hydrogen has to go into the moth. I kind of think about it as a sort of molecular sponge, so it just soaks everything up. The metal organic frameworks are made of metal absorption sites, so the metal part, and then organic linkers. These are aromatic linkers. In our materials, they're usually benzene rings. And the really great thing and exciting thing about moths is that you can potentially build a certain moth to do a certain application. So you can pick your metal and pick your linker and try to optimize your structure. And so what we're trying to do is figure out what different metals do, what different linkers do, to sort of give guidance for chemists to build new structures. So this is the material that we're working on. It's known as MOF74. It's a name that doesn't really give you much information, but so MOF74 has this hexagonal structure. These are the metal sites, and you can see the little green dots are where the hydrogen binds. So we're specifically studying hydrogen. MOF74 is an isostructural series. This means you can build the same structure and just substitute out different types of metals. So this gives you a really nice system to study some reaction or some binding of hydrogen as a function of metal. The special thing about MOF74 is it has this open metal site. So you have your metal here in green, it's bonded to 5 other atoms, and it really wants to bond to 6. So this gives it a higher binding energy, around 10 kilojoules per mole, instead of like 5 for other MOFs. So what is catalyzation? A catalyst is something that increases the rate of a chemical reaction. So what it does is you have this energy barrier here, and your catalyst allows you to bypass the energy barrier. In our example, this would be trying to pull hydrogen apart. So it takes a lot of energy, like thousands of Kelvin, to dissociate hydrogen, to pull them apart. But we're doing it at much less energy. We don't need to heat the system. We're doing it at room temperature. So hydrogen, it's like a spring. You can model it as a simple harmonic oscillator, so it has some vibration. And we observe this vibration as energy levels in our infrared spectrum. So you see different peaks at different frequencies, and that tells you the vibrational levels of the hydrogen. We can figure out what the composition of a gas is that's in the MOF by looking at different frequencies. So the frequency goes as root K over M, so K being the spring constant and M being the mass. So you can see that hydrogen has a different frequency as deuterium, since deuterium has a proton and a neutron, versus Hg, so a hydrogen atom bonded to a deuterium atom. And furthermore, the MOF also changes the vibration, so we can figure out what the binding energy is by how much it changes the spring constant, basically. So We mainly use infrared spectroscopy, and if you know anything about hydrogen and infrared spectroscopy, you know that like no one ever does hydrogen with infrared spectroscopy. Hydrogen has no dipole moment, so the charge is uniformly distributed, so you never see it. But when we put the hydrogen into the moth induces a dipole moment, so it sloshes the charge over to one side, basically, and then we can see it in the infrared. So this is actually a feature of what we do rather than a problem, because we can only see the gas that sticks to the moth, and we're not confused by everything that's not sticking, things that are in gas phase versus absorbed phase. So even though we've induced a dipole moment, the signal from the hydrogen is still pretty weak, so we have to use this technique called diffuse reflectance infrared spectroscopy, basically to amplify our signal. So that's a schematic of the mirrors and how that works to bounce the light around in the sample to get a higher signal. So this is our box or cryostat. It's pretty standard to do infrared spectroscopy on gases or materials, but what's unusual about what we do is we do things cold. So what that gets you is much sharper spectrum. As you cool things down, you get everything in ground state, and your peaks like sharpen up a lot, so your data gets a lot better. Also, gas doesn't stick to moths at room temperature, so you have to heat it, cool it down rather to about like 150, 140, or 77 Kelvin, liquid nitrogen temperature, to get anything to stick. So here are some pictures of the lab. This is the spectrometer with the cryostat on top of it. Here's what our sample actually looks like. It's just a powder, very tiny amount of powder, and so that's a sample holder. We have to do everything under an atmosphere of argon because the sample is very, very air sensitive. So if you exposed it to air, water from the air would just stick to all the metal sites, and then you'd never get hydrogen to stick. So we do everything in a glove box and then attach this dome to the sample, and it has windows here so that the infrared red light can go through. So getting back to our results. So we were studying mixtures of hydrogen and deuterium, mainly to do like selectivity work. We weren't expecting to see this formation. So we were doing this experiment, we got a nice peak in the deuterium region, a nice peak in the hydrogen region, we had a 50-50 mixture. And then we decided to be done for the day, valved the system shut, so we had the gas in, and just left it. So it warmed back up to room temperature from about 77 Kelvin. We came back the next day, we cooled down, and we got this. So that's a very clear peak in the HG region. So obviously something's happened, like the gases have separated and a hydrogen atom has been able to bond to a deuterium atom. We weren't expecting this because the interactions, the sticking of the hydrogen molecules to the moth are via a weak van der Waals interaction, so a dipole-dipole force, and you wouldn't expect that to be strong enough to pull hydrogen apart. We wanted to get a sense of how quickly this was happening. Since we can only see things when they're cold, we can't see the conversion. So we took our sample over to a professor in the chemistry department who has a mass spec, and he did this. So you can see that the signal, this is a plot of the fractional HG composition in the gas versus time. It comes up pretty quickly to about 50%, which is good. It's what you'd expect statistically. We wanted to make sure that it wasn't just metal impurities, because metal surfaces can catalyze hydrogen on their own. So what we did is we exposed the sample to air, and then so water would go to all the metal sites, and we repeated it, and we got much less rate of HG formation. So there's still a little bit. You'd expect that a few metals might still be open and the reaction would still happen, but the rate is much decreased. Then we just wanted to make sure that we could recover our sample. We heated it up to get all the water out, and we got back to what we had before. So in summary, it's pretty surprising that this catalyzation is happening, and it's exciting because this is the first evidence that the binding is strong enough for that dissociation would actually happen in a moth. It happens in a pretty short time scale, a few minutes, so that's good, it goes quickly. So far we've observed it in the magnesium, the nickel, and cobalt versions of MOF74. Interestingly, it doesn't occur in materials without that open site. the open metal, so materials that are bonded to 6 different atoms where the metal is, that doesn't happen, so that's cool. And it also doesn't happen in materials that are an expanded version of MOF-74, where basically the metals are further apart because there are 2 benzene rings instead of 1. In standard methods of catalyzing hydrogen on metal surfaces, you have to heat it up to get the atomic hydrogen to come off. In our method, it happens at room temperature, so you don't need to do anything. In the future, we'd like to investigate the rest of the isostructural series, so the rest of the metals. We want to probe the mechanism by studying different variations of MOF-74. We can build different versions. And we also want to study the catalyzation as a function of temperature to try to get to what temperature the dissociation is happening at. I would like to thank my advisors, Stephen Fitzgerald, Professor Rousel, who made our samples, Professor Elrod, who has mass spec, my lab mate, Elizabeth Gilmore, Bill Martin for machine, Bill Miller for electronics, and NSF Brand for Francis work.
Questions for Jocienne?
Does the 74 actually mean something, or is it just the 74th MOF?
The naming conventions are terrible for MOFs, so it doesn't really mean that much. There's different names that chemists use more that describe more of what the structure is, so those are more meaningful, but not really.
Is this just investigation into the structure of different MOFs, or is there actually a practical use for them?
There is a practical, so a lot of the research is done in hydrogen storage, so trying to get a MOF that sticks hydrogen better. We've also been doing a lot of work in separating hydrogen and deuterium, because deuterium is useful like for nuclear reactors and stuff. This might be useful, like catalyzing hydrogen is something that's important, it's done a lot, but this is very preliminary work. But the separation is, I think, the most promising for actual practical applications.
So how confident are you that you understand the nature of the bonding of the hydrogen to the metal sites, since you were surprised by it?
I think that we understand the bonding cold pretty well. It's what happens when you heat it up to room temperature that's we don't understand so well. Hydrogen will dissociate just on metal surfaces, so it might be something like that. We can study things when they're cold. It's when they're room temperature where we can't get an infrared spectrum that it's more complicated.
Was the box, the experimental box, built at Oberlin?
Yeah, that was built by a few years ago. Another student, my advisors.
All right, let's thank our speaker again.